Hey everyone, welcome to this explainer. Today, we're going on a guided visual tour through the complex quantum mechanics and physical chemistry behind NMR spectroscopy. We're going to break down exactly how we can peer into the invisible structures of molecules using our presentation today. It's an absolutely fascinating topic, so let's just get right into it.
All right, looking at our roadmap for today's discussion, we've got 1. Basics of nuclear spin. 2. Magnets and energy states. 3. Achieving magnetic resonance. 4. Understanding chemical shift. 5. The TMS reference standard. And 6. Molecular structure and shielding.
Section 1. Basics of nuclear spin.
So what are we actually doing here? Well, as we've defined it, nuclear magnetic resonance essentially looks at how radio frequency waves interact with the magnetic energy levels of a molecule's nuclei. We aren't breaking chemical bonds, and we definitely aren't destroying the sample. We are simply, gently, coaxing transitions between energy levels.
Notice exactly where this happens on the electromagnetic spectrum. It's way, way off to the right. The radio frequency energy we're using here is actually tiny compared to high-energy waves like X-rays or gamma rays. It's got a much longer wavelength and a super low frequency. And because this radio frequency energy is so incredibly small, it doesn't just wildly vibrate or excite the whole atom. Instead, it perfectly affects the nucleus. Now, certain nuclei behave as if they're spinning, possessing an intrinsic quantum property predictably called nuclear spin. It acts a whole lot like a tiny, charged spinning top. But here's the catch. Not all elements can be analyzed using NMR. To be NMR active and actually possess this spin property, an element has to have either an odd atomic mass or an odd atomic number. Take a look at carbon-12 in the table there. Even mass, even number, zero spin. It's completely invisible to us. But hydrogen-1 and carbon-13, they've got those odd numbers, giving them a half-integer spin. They are absolutely the stars of the show. Section 2. Magnets and energy states. Okay, so any moving electrical charge creates a magnetic field, right? That means a positively charged spinning nucleus generates its own tiny magnetic moment vector. You can see it represented by that arrow, which gives us two distinct spin states to work with, a +1/2 state and a -1/2 state. Normally, out in the wild, these are totally random and equal in energy. But things change dramatically when we put our sample into the spectrometer. When we blast these tiny proton magnets with a massive external magnetic field, all that randomness just vanishes. They're forced to make a choice. They either align with the external field in what we call the alpha state, or they fight against it in the beta state. Check out how this external magnet, labeled B0 here, literally separates our protons into two different energy levels. Going with the flow and aligning with the giant magnet takes way less effort, so the alpha state drops down to a lower energy level. Fighting it, however, pushes that unaligned beta state up to a higher energy level. Section 3. Achieving magnetic resonance. Now we need to define the R in NMR, resonance. Resonance occurs when the frequency of the absorbed radio wave energy perfectly matches the precession frequency of the nucleus. We are talking about an absolute, precise energetic match here. So when a photon of radio frequency radiation hits that lower energy spinning proton with the exact right amount of juice to bridge the gap between those split energy levels, it gets absorbed. This literally forces the spinning proton to flip its alignment from the lower state to the higher state, fighting the magnetic field. That flip, that is the exact moment of resonance. But wait a second. This brings up a really fascinating question. If every single hydrogen proton is physically identical, and every proton flips exactly the same way in a magnetic field, shouldn't they all just absorb the exact same frequency? And if they do, how in the world does this actually help us identify complex multi-atom molecules? Section 4. Understanding chemical shift. This is where we transition from quantum physics into highly practical chemistry to answer that exact question. The real utility of NMR, the secret sauce if you will, is that in a real molecule, protons aren't just floating isolated in a vacuum. They are surrounded by clouds of valence electrons. And those electron clouds vary depending on the proton's specific atomic neighbors. An aromatic proton is in a slightly different electronic environment than an aliphatic one, causing them to absorb at slightly different field strengths. Let's look at this comparison. The red line here represents a hypothetical bare, naked proton absorbing energy. But that blue line? That represents a proton buried inside an organic molecule, heavily shielded by its surrounding electrons.
Because of this electron shield, it actually takes a stronger external magnetic field to make it resonate, which causes its signal to shift upfield, over to the right. Section 5. The TMS reference standard. So if every single proton shifts differently depending on its electron shield, how do we measure this accurately across different labs and machines? We need a universal ruler. Enter TMS, or tetramethylsilane. Look at that central silicon atom surrounded by 4 methyl groups. It turns out these protons are incredibly well shielded, appearing way upfield on the readout. Chemists universally adopted TMS as the ultimate zero-point baseline. In modern NMR, we simply measure how far downfield every other peak shifts away from this TMS zero line. To make sure everyone is speaking the exact same language, we calculate the chemical shift using the formula shown here. By dividing the shift in hertz by the specific spectrometer's operating frequency in megahertz, we get a standardized parts per million, or ppm, value. This brilliant little piece of math ensures that whether you run your sample on a standard 300 megahertz machine or a massive multi-million-dollar 900 megahertz supermagnet, your parts per million graph is going to look the exact same. Section 6. Molecular structure and shielding. For our final step today, let's look at exactly how we use these shifted, standardized parts per million signals to map out an unknown molecular structure. As you can see, surrounding electrons create their own tiny opposing magnetic field. That's the shielding effect on the left. But look at the table on the right. If a proton is sitting next to a highly electronegative atom, like fluorine or oxygen, that greedy neighbor pulls the electron cloud away. This de-shields the proton, leaving it exposed to the main magnet and forcing its resonance signal to dramatically shift downfield to a higher parts per million value. And it's not just the neighboring elements, it's the actual bonds themselves. You can see right here how the type of carbon hybridization changes the shielding entirely. A proton on an sp3 hybridized methyl group shows up way upfield, near 0.9 ppm. But look at the sp2 hybridized double bond, sitting near 5.3 ppm. And that aromatic benzene ring, its unique electron ring current massively de-shields the protons, throwing them all the way downfield to 7.3 ppm. You can literally distinguish between single bonds, double bonds, or aromatic rings just by glancing at where the peaks land on your chart.
It truly is incredible. By simply taking a sample, applying a giant external magnetic field, and hitting it with a low-energy radio wave, you are literally talking to the quantum spin states of atomic nuclei. You've unlocked the power to read the shielding environments of valence electrons and map the otherwise invisible structural world of organic chemistry. So I'll leave you with this question. Armed with this incredible visual tool of NMR spectroscopy, what complex molecules will you decode next?